Hello, my name is David Hurd, and this is my Lab 1 for constant velocity motion. To begin, I want to go over some principles that will be used throughout this lab, namely Newton's first and second law. Newton's first law, the law of inertia, states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon on an outside force. This means that our object, which will be moving at constant velocity, will have zero net force on it. Newton's second law, the momentum principle, states that any change in momentum is proportional to the net force, as you can see in these equations. We'll also be using the position update and the velocity update formula within the code, which here you can see the equations and their respective places in the code. The initial conditions for this experiment are that the x position, or the x vector, will be 0, 0, 0, but the full vector will be 0. The velocity vector will be 0.35 in the x direction with 0 in the y and z. The purpose of this lab is to compare an ideal computational model, which we'll create using Python to get that model, with a real-world scenario which we will track and observe using a tracker app for a constant velocity motion object. The tracker app will give both the initial conditions and the real path of the water bottle that we will use, and that we will use those conditions to make a computational model. The predicted position of the water bottle and the observed position will be slightly different for a number of reasons we'll go into later. This is the object that we are studying. Here is the tracker model, where the system is the water bottle, the surroundings are the floor, the earth, and me, and we get this data. As you can see, it may look a little rough, but overall it is a straight line because of the constant velocity, and the slope of a position to time graph will be the velocity. Now here's the computational model, and as you can see it's even more straight, but it looks roughly the same. However, when you put one over the other, you notice that it's slightly different. The slope of the observed position seems to be greater later on, and that's because the velocity is actually changing slightly in the observed model in the tracker app, while the predicted one is consistent through. However, they're both starting at the same position. Now, this could be for a number of reasons, but most likely it could be due to air resistance and drag or friction that we didn't account for, that we thought was negligible, that was actually not. However, the main reason is most likely human error, and that when I either A, rolled the water bottle, I made it so that it didn't perfectly line up with the camera, or B, when I was tracking it in the app, I may have made mistakes when marking the positions of the water bottle throughout the different frames. Now, what if we flipped the axes of the x-axis? Well, visually, the graph would be flipped, as you can see in this example, but every single value and the result of the overall thing would be identical, just with opposite sign. Now, what does it mean with all these different forces, and how can we add them up? And the truth is that we cannot know every single force acting on the water bottle, but we can know the main ones, which would be gravity, the normal force, friction, and drag. And the friction and drag are going to be very negligible, at least that's what we thought. But based off of our results, we can tell that they might be more important than we thought. However, overall, there was a mostly net zero force on the object.